this class, we will focus in large part on the sampling distribution of a sample mean. So that is like, how does X bar move around from one group to the next? So this is the particular sampling distribution that we'll be working with most frequently. So just to create the context of this, so that you get some sort of a feel of what sampling distributions are about, we'll do an activity on Wednesday that'll hopefully help with this too. You can imagine if we're interested in what the sampling distribution of the average of 5 heights randomly chosen from this class is, the way we would simulate that is basically all of you are our population, and we would randomly choose 5 of you and take your average height. And then we could go and randomly choose 5 different people and take their average height. And then randomly choose 5 new people and take their average height. And then randomly choose 5 new people and take their average height. And we could look at how those averages fluctuate. Does that make sense? So that's the sampling distribution. The sampling distribution is, how does the average of 5 individuals randomly chosen change from one group of 5 to the next group of 5? That idea. So, and that's getting at what a sampling distribution is about. And why this matters will hopefully make sense maybe closer to exam 2. But for right now, we're just focusing on what is a sampling distribution? What does it get us? So, So there are 2 mathematical theorems that tell us some nice properties about this sampling distribution, like what happens if we were to carry that process through. And here's what one of the theorems, which hopefully makes a lot of sense, is called the law of large numbers. Okay. And what the law of large numbers tells us is hopefully something that feels very common sense. If you choose a larger sample size, the mean that you pull will converge to the true mean of your population. Right? So if we have an actual mean height in this room, choosing a sample size of 5 is likely to be farther away than choosing the mean of 20. If that makes sense. And if I choose 30, then it should get even closer. If I choose 35, then it should get even closer.
You repeat that?
Yeah, I'll actually write it out. So it says, I guess mathematically it's kind of nice. So it says the limit of X bar as n approaches infinity is so that is, if I choose a larger and larger sample size from which I compute X bar, that should converge to the true population. Is that idea?
So a good example would be like, shit.
That's not a very good example.
Let's say you got like 50 gumballs, and you take the mean of those 50 gumballs. Let's say you're going to choose
Well, I mean, so it just says that your sample mean is going to be closer to the population mean the larger your sample size is, right? So if I want to know the true average house price in Denver, and you give me 10 randomly chosen houses, that average house price is probably going to be farther away than someone else who gives me 200 randomly chosen house prices.
Okay.
Right? That 200 is a better example of what the true average house price is than the one drawn from a sample of 10.
Got it.
Yeah.
There's n and the arrow and what is the
Yeah, so basically this says the limit as n approaches infinity, so that's as our sample size goes to infinity, of x bar is the population mean, right? So basically our sample mean will converge to the population mean as the sample size increases.
So like the more accurate almost.
Yeah, exactly. You're likely to get a sample mean that is a better representation of the population. It's more accurate.
So the n represents the sample mean?
The n represents your sample size. X bar represents the sample.
you said? Just before the sample mean will.
Yeah, so if we choose a large enough sample, or so, sorry, larger sample size. So it says, okay. So basically, the larger the sample size you choose, the closer you should get to the population mean. Right. Hopefully that's like fairly pretty consistent. Yeah. It's like, oh, somebody got the doctorate for that. So this is the first one. This is the first of those two theorems. And so the law of large numbers basically tells us that the sample mean should get closer to the population mean if we take a larger sample size, which means taking larger sample sizes is good for the purpose of like having accurate estimates. The second one, which is maybe a little bit more confusing, and this is the one that we'll illustrate on Wednesday. We'll go through an example that hopefully shows what this is talking about. But this one's called the central limit theorem. And I'll frequently abbreviate it as the CLT. I wouldn't mind if you do the same. So, what the central limit theorem says. So the central limit theorem says if we choose a large enough sample size, right? So if we choose n large enough, the central limit theorem tells us that if we choose a large enough sample size, our sample mean will follow a normal distribution, even if the original data does not follow a normal distribution. It could be right skewed or left skewed, any other shape. And our sample mean will still follow a normal distribution as long as we choose a large enough sample size. This one's a little bit harder to like that. your head around.
So could it just be summed up as larger the sample size, the more likely the distribution?
Will follow in the home. That's true. Yeah, that's certainly true. And it really depends on the distribution of your original data, on like what a large enough sample size is based. In this class, we'll use n greater than or equal to 30. So if we choose a sample size of larger than 30, then you can assume that the central limit theorem has kicked in. That's just like put in lots of interest aspect books everywhere. In practice, I usually just simulate it. So simulate, great. If I have some set of data, I can just simulate whatever. I could randomly draw from that set of data and then compute the mean.